so I know we've talked about the graphs of sine and cosine, but there are some things that kind of modify them. We didn't really talk about the graphs of secant, cosecant, tangent, and cotangent. So let me throw those at you guys relatively quickly, and then we'll talk about how you can kind of modify their graphs. So we're just going to put them on, like, we're going to go very kind of fast. So here's the graph of sine. Sine x looks like this. It's got a period of 2 pi, cut it up into 4 equal sections, height of 1, -1, middle, top, middle, bottom, middle. So sine looks like this, and then cosine same sort of deal. Starts up here, top, middle, bottom, middle, top. That's what sine and cosine look like. And before we move on to the other four, let me talk about kind of how you can modify them. So, gosh, yeah. There's kind of two things often that we do for trig functions. We either change the period or we change the amplitude. You can also shift them left or right or up or down, but that's kind of less of what's going on in these classes. So, for example, if I wanted to graph, say, I don't know, y equal to sine of 3x, the new period would be 2 pi divided by 3. It's always divided by whatever that coefficient is there for sine, for all of them actually. So sine 3x, the way I kind of look at that 3 is you're going to get 3 times as many full periods in the same length. So from 0 to 2 pi, you would actually get 3 full periods. I'm going to split this up. So there's 2 pi over 3. So there's my 2 pi over 3. And then I'm going to break that up into, so it's going to get kind of smushed in here, right? Break that into 4 equal quadrants, still with a height of 1. And then I know that sine starts in the middle and then goes up in the middle and then down in the middle. So it starts in the middle and then up and then middle and then down and then in the middle. So there's one period of sine of 3x. Right? It got smooshed in. It got horizontally compressed is the more technical way of saying that. Or we could look at something like, I don't know, y equal to 4 cosine of 2/3 x. So this function would get stretched vertically by a factor of 4, right? The amplitude. See, I think I can fit this in here. The amplitude would equal 4. That just means how far from the middle above and how far from the middle below we're going to go. See, I think I can make this fit, sure. So we're going to go up 1, 2, 3, 4, down 1, 2, 3, 4. Sure, yeah, we'll make it fit. And then the period. So again, here the period was 2 pi divided by the coefficient of x. Here the period is going to be 2 pi divided by the coefficient of x. So giving myself a little more room. The period for this function is going to be 2 pi divided by 2/3, which is the same as 2 pi times the reciprocal 3/2. The 2's cancel, you get a period of 3 pi. Yeah, totally. Yes, Marshall. Yeah, exactly. So yeah, so you're right. I didn't actually show that work here, but if what I could really do, like going back for just a second, if I wanted to, I could definitely take my 2 pi over 3, divide it by 4, which is the same as multiplying it by 1/4, to get 2 pi over 12, which is pi over 6. And then each of these important points are 0, and then x equals pi over 6, x equals 2 pi over 6, x equals 3 pi over 6, x equals 4 pi over 6. It's kind of a lot to write on the graph, but you're totally right. Like usually I call them the 5 important x values. Your x sub 0 would be 0, your x1 would be pi over 6, your x2 would be 2 pi over 6, which you could reduce. x3 would be 3 pi over 6, x4 would be 4 pi over 6, which is 2 pi over 3, which is how far we get. Same deal here, right? You could find you can divide this by 4. So 1/4 of your period is equal to 3 pi over 4. And then your important points are going to be at 3 pi over 4. And then add another one to get 6 pi over 4. And I know it's hard to see what I'm writing here. Add another one to get 9 pi over 4. Add another one to get 12 pi over 4, which is 3 pi. Right, so you're breaking it up into 4 equal quadrants. I'm not dividing by 1/4, Diana. I'm multiplying by 1/4, which is the same as dividing by 4. So I'm just doing, right, I'm doing the period divided by 4 is equal to the same thing as 1/4 times the period. And the reason we're doing, so the reason we divide by 4 or multiply by 1/4 is because most trig functions, kind of the important points or the places where like you hit the tops and the bottoms and the middles, those happen at each of the ends of the quadrants. So what we're saying here is usually a full period would be 0 to 2 pi. And from 0 to 2 pi, every quadrant, right? So like, I know I erased my sine and cosine graph already, right? 0, you start at 0, and then pi over 2, the next quadrant, you get to the top, and then pi, and then 3 pi over 2, and then 2 pi. The difference here is that now our period is 3 pi. So we divide 3 pi up into 4 equal quadrants. So from 0 to 3 pi over 4 is the first quadrant. From 3 pi over 4 to 6 pi over 4 is the second quadrant. From 6 pi over 4 to 9 pi over 4 is the third quadrant. And from 9 pi over 4 to 12 pi over 4 is the fourth quadrant. And in those 4 quadrants, you get the usual shape for the cosine graph. So cosine is going to start up at the top. And then when you get to the end of the first quadrant, you're going to be the middle. The end of the second quadrant, you're going to be down at the bottom. End of the third quadrant, back to the middle. End of the fourth quadrant, which is 1 full period, about 4 quarters is 1 whole, you're back to the top. I would also encourage everyone to take advantage of the use of Desmos and definitely look at the graphs of these things on Desmos if you're ever unsure about what you're graphing. So these are how we modify the graphs of sine and cosine, right? The period is always 2 pi divided by the coefficient of x here. And then if you want to find the 4 quadrants, you divide that period by 4 and then mark each of those. And then the amplitude is just how much we're going to stretch or compress it. So whatever this number out here is, if it's bigger than 1, we're going to stretch it. If it's smaller than 1, we're going to compress it. There are 4 other trig functions, though. I do feel like we should mention them. So there's tangent and cotangent. So when I'm graphing tangent and cotangent, there's really kind of just one part that I graph. So if I'm going to graph tangent of x, it's always going to look like this. Vertical asymptotes is pi over 2 and negative pi over 2. And it hits right there, and it does this. If I was graphing more points, the other points I would graph would be at pi over 4, comma 1, and negative pi over 4, comma negative 1. And then the rest of the graph, so that's 1 full period, and that's actually something interesting about tangent versus the other 4 trig functions, is for tangent and cotangent, the period is equal to just pi. And then you can graph more of it by just repeating that. So if I have a vertical asymptote pi over 2, I'm also going to have a vertical asymptote pi away, which is going to be pi over 2 plus pi, which is 3 pi over 2. And it's just going to have the same exact shape. And same to the left, same to the right. And then cotangent is very similar. If we're going to graph cotangent of x, it also has a period of pi, but it has the vertical asymptotes where, so think about it this way, tangent and cotangent are reciprocals of each other. So if tangent is equal to 0, cotangent is the reciprocal of 0, which is undefined. So cotangent is going to have the vertical asymptotes where the tangent has the x-intercepts. This pen is dying. Let's see this better. So, that's a little better.
x equal to pi, x equal to negative pi. And cotangent looks like this. So it's 0 here, and it goes down from left to right. But it essentially, I mean, not essentially, it is literally the tangent graph shifted pi over 2 and then flipped over. Can you go ahead? Yeah, totally. Yes, we can do a graph of tangent or cotangent of a different value. So I'll say this though, before I do it, so the graphs are going to look the same. They're just going to be squashed or stretched depending on what's multiplying x. So let's do 2 examples. Let's do, but again, so again, I'll remind everybody, when I'm graphing some other trig, some modification of trig function, I'm keeping the original graphs in mind and then just kind of manipulating them. For tangent and cotangent, I'm also less likely, like for the sine and cosine one, I like to find like the 5 points, break the period up into 4 equal sections and do, middle, top, middle, bottom, or whatever. For tangent, less of that really. For tangent, the only points we usually really care about graphing are, well, the asymptotes, which aren't points, yes. And then in the middle of the asymptotes where you cross the x-axis. Sometimes we add in these extra spots here. I'm less likely to. So let's graph 2 of these. Let's do say y equal to tangent of 3x. So here's what's going to happen. The period is going to be not 2 pi divided by 3, right? For tangent and cotangent, it's pi divided by whatever the coefficient of x is, which is 3 in this case. Tangent, so for tangent, it's nice because you're kind of in the middle. Tangent of 0 is 0. And then you need a full period. So to get a full period, you need to go half of this distance to either side to get the vertical asymptotes. So I guess I should try and draw it so it doesn't look quite as big, but honestly, like I usually draw my graphs kind of the same. So right, that's how far I went to the right when I was pretending like it was pi over 2. I guess I could make it a little bit smaller, but I want to make it so I can actually still graph my graph. So there's my vertical asymptotes they're not at pi over 3, right? They're at pi over 6, which is half of pi over 3. So this one's at pi over 6. This one's at negative pi over 6. And then my next x-intercept, that would be at pi over 3, right? Because again, the graph should repeat itself every full period. So if you have an x-intercept at 0, you should also have an x-intercept pi over 3 away. You should also have an x-intercept another pi over 3 away at 2 pi over 3. And then you should have another vertical asymptote in between them. So this is going to look like this. And it just keeps going. And you would also have another, vertical asymptote to the left here. So this point here would be negative pi over 3. And this would be a vertical asymptote. Usually you're only asked to graph like 1 or maybe 2 full periods of a trig function. Here we graphed 4 of them. So that's how you would graph something like tangent of 3x. If I wanted to graph on the other side, maybe, I don't know. Let's grab this pen here. Y equal to your cotangent of x over 2. So now the period is going to equal pi divided by the coefficient of x, and the coefficient of x is 1/2. Pi divided by 1/2 is 2 pi. Cotangent has the asymptote not like, so I should say tangent has the intercept on the x-axis at the origin, whereas cotangent has the vertical asymptote on the origin. So this one's going to look like this. You have a vertical asymptote there. And then the next vertical asymptote should be 1 full period away. So over here at maybe 2 pi. That's where my next vertical asymptote is going to be. And then there's also going to be one to the left. Sure, we can go that far to the left. Why not? And then cotangent, instead of going up from left to right, goes down from left to right. But it has the same shape. So it's going to have intercepts at pi and at negative pi. Let's do this kind of deal. That's kind of it. All right, let's do the last two because the last two are interesting. Oh, actually, let me see. Yeah, let's see. Somebody asked me for one of these for sure. Maybe not. So let me ask before I do them. Do we want to see graphs of cosecant and secant? I'm happy to do them, but only if people actually want to see them. Yes, please. All right, let's do it. So my kind of tip for graphing secant and cosecant is to actually first graph sine or cosine. So if I was going to graph y equal to secant of x, I would remember that it's actually equal to 1 over cosine of x. So I'm not actually going to graph cosine. I'm going to kind of just graph the outline of cosine. So I know the period's still going to be 2 pi. And look, I know I'm not saying it, but I am breaking that up into quadrants, right? That's pi over 2, pi, 3 pi over 2. Here's another quadrant, negative pi over 2. And I know that cosine, so I'm not actually graphing cosine, but cosine would start it right there. And then cosine of pi over 2 is 0. Cosine of pi is negative 1. Cosine of 3 pi over 2 is 0. Cosine of 2 pi is back to 1. So cosine would look like this. And here's the thing. Secant is the reciprocal, meaning, well, the reciprocal of 1 is 1, right? If cosine of 0 is equal to 1, 1 over 1 is also 1. And then here's what's going to happen. As the cosine values get smaller, the reciprocal or the inverse gets larger, right? That's what it means for things to have an inverse relationship. As one of them gets small, the other one gets big, and vice versa. So as the cosine values get smaller and smaller and smaller, closer to 0, the secant values get super duper large. And so wherever cosine is equal to 0, secant is going to have a vertical asymptote. So the only thing we have to determine is whether it's positive or negative. So over here, cosine of pi is negative 1. 1 divided by negative 1 is also negative 1. So secant of pi is also negative 1. And then as the cosine graph gets closer to the x-axis, the secant graph gets further away. So the way I kind of think about graphing this is that you're kind of taking the point where they meet and then kind of flipping this over away from the x-axis. It's not exactly a perfect analogy, but it kind of works. Right? So instead of going down this way, I'm flipping it up and going up this way. Same deal here, right? They meet at this point here, but when I go this way, I'm going to go that way. When I go this way, I'm going to go that way. Just a word of warning here, these are not parabolas. I know they kind of have a kind of parabolic look, but parabolas don't have vertical asymptotes. So just be aware, right? They're not actually parabolas, even though you can kind of draw them like they're parabolas. Cosecant, I graph very much the same way. So if I was going to graph y equal to cosecant of x, let me kind of show you my abbreviated version of this, how I actually kind of do it. So if I was graphing cosecant, I would think about sine. I'm not actually going to plot out the sine graph, but I'm going to think about what sine does. So let's see. So for cosecant, I'm still using the same sort of quadrants. Negative pi over 2, pi over 2, pi, 3 pi over 2, 2 pi. And I know that sine, if I was graphing sine, which cosecant is the reciprocal of, it's 1 over sine. Sine would be sine of 0 is 0, and then sine of pi over 2 is 1. and then sine of negative pi, sorry, 3 pi over 2, sorry, of pi is 0, and 3 pi over 2 is negative 1, and then 2 pi is 0. And then I'm going to say, well, I know that wherever the sine values are 0, the cosecant values are having vertical asymptotes. So vertical asymptote here, vertical asymptote at pi, vertical asymptote at 2 pi. And also negative pi over here, let's say. And then I know that wherever sine is equal to 1 or negative 1, so is cosecant, right? If sine is 1, 1 over 1 is 1. If sine is negative 1, 1 over negative 1 is negative 1. So these points here that I've graphed actually are points on the graph. And then we go away, right? Instead of going up towards the x-axis, we go away from the x-axis. So instead of going down like that, we're going to go up like that. So there's my not great, but good enough cosecant graph. Yeah, and this is actually kind of how I really graph sine, or sorry, secant and cosecant, even if they're kind of compressed or stretched or amplitude is changed. So 2 more examples, and then I think I'm going to call it a day on the trig graphing. Although there's certainly some questions that have trig stuff in them. So we're not done with trig, we're just done with the graphing part. So let's say I wanted to graph y equal to, sure, 3 secant of 2x. All right. So here's what I want to remind everybody about. The smallest that secant can be, the smallest positive value secant can have is 1, right? Secant goes as low as 1, but there's no values between negative 1 and 0. So the smallest that 3 times secant can be and still be positive is going to be positive 3. So that 3 is going to kind of stretch things away from the x-axis. So here's kind of the nice thing about this. My idea of drawing cosine or sine and then kind of reflecting it away still totally works. So actually, I'm going to think about what 3 cosine of 2x looks like. Well, I know what that is. I know the amplitude is 3, and the period is 2 pi divided by 2, which is pi. So, this way. Let's give ourselves some room. Let's say this is pi, this is 2 pi. I'm cutting these periods into quarters, although I'm not writing all the values, right? Here's my period pi, cut up into 1, 2, right, into quarters. And let's go negative as well. Okay, so I know that, I also said my amplitude was 3. So let's see, so, okay. Pi is about 3, so sure, there's about 3. I will stress also that if you're graphing these, you don't have to make your x and y axes have exactly the same scale. They can be wildly different, that's okay. So here's what cosine would look like. 3 cosine of 2x would start up here. And the next important value would be here. And then the next one would be down at the bottom, and then back to the middle, and then back to the top. I really only care about what's happening here and here. So these are going to actually be points on my secant graph, right? Because if cosine of 0 is 1, 3 times cosine of 0 is 3. But if cosine of 0 is 1, secant of 0 is also 1, and 3 times 1 is still 3. So the same kind of thing applies. What I can do is say, all right, well, when cosine is 0, secant's going to have a vertical asymptote. And so I'm going to get, right, here's a point on the graph, and it's going to go this way instead of going that way. And here's a point on the graph, and it's going to go this way and this way. I'm trying to use the right colors here. Yes, you could totally have graphed the cosine graph if you wanted to, right? Here's what the cosine graph would look like in green. It would start here, and then it would go down to 0, and then down to -3, and then back up to 0, and then back up to 3, and then it would just keep doing it over and over again. Right, and so I've taken those cosine graphs and kind of flipped them away from the x-axis, right? This one, like that. That's really, really how I think about graphing secant. Is I think about what the cosine graph looks like, and then kind of take the top parts and flip them up, take the bottom parts and flip them down. It's kind of weird, but it totally works. All right. I feel like it's enough trig graphing, I hope. For now, we can always do more later. Let us get into some examples of derivatives, and then we'll hit up some marginals and some motion stuff close to the end. All right. Yeah, you guys had lots of questions about derivatives, which is good. Okay. Yeah, let's see if I've got any other not terrible pens over here. Problem is I try to get all the life out of the pen I can before I give it some new ink. So I'm trying to not waste the pens. They do actually cost money. They are a limited resource. I don't have to pay for them. Someone in our department is paying for them, or the school is paying for them. So I should try to use them efficiently. All right, so let's look at. Sure, let's start with this one. Let's find the equation of the line tangent to f of x equal to 2 sine x cosine x at x equal to 3 pi over 2. Interesting. This might not be a very interesting answer. That's okay. There's actually 2 ways you can do this problem. Let's talk about so I'm going to show you kind of what I think of as the standard way, and then I'll talk about the maybe easier way if you see a thing. So to find the equation of tangent line, we need 2 things. We need a point and a slope. The point, well, we know the x coordinate is 3 pi over 2. It's 3 pi over 2, comma, whatever the y value is. Sometimes if you're feeling like you don't want to find a thing, but you still want the person who's grading your work to know that you know how to do a thing, I would write maybe, well, I know the other point is f of 3 pi over 2. Yes, you should actually find that, but if you were taking a test and you were running out of time, you could write the equation like once you found the slope, you'd be like, okay, the equation is y minus f of 3 pi over 2 equals whatever your slope is times x minus 3 pi over 2. Yeah, maybe you're going to lose a point, but you're still going to get some partial credit for showing that you knew what it should have been, even though you didn't find it. So f of 3 pi over 2 is, it's going to be 2 times sine of 3 pi over 2 times cosine of 3 pi over 2. And here's what I definitely know. One of those is 0, right? 3 pi over 2 is one of the quadrantal angles, right? It's an angle that occurs on one of the axes. 0 pi, wow. 0 pi over 2 pi, 3 pi over 2, and 2 pi. And then, right, the angle, the sine and cosines are, this is 1, 0, 0, 1, negative 1, 0, 0, negative 1. Even if you didn't remember which one was sine and cosine, you'd be like, well, one of those is sine, one of those is cosine, so one of them has to be 0. So this is equal to 0. It is that cosine is the x coordinate and sine is the y coordinate, right? It's alphabetical. Cosine comes before sine, x comes before y. So cosine, sine. So cosine of 3 pi over 2 is 0, which means this whole thing is 0. So our point is 3 pi over 2, comma 0. Our slope, we have to take the derivative. And so I'm going to take the derivative, what seems like the obvious way, by just using the product rule. And you can either think of the 2 just living out in front. I often, when I have a constant with a product rule, I kind of like to attach it to one of the pieces. So I'm going to think of this as 2 sine x times cosine x when I do the product rule. So my derivative is, so the derivative of 2 sine x is 2 cosine x times the other piece, which is cosine x, plus, now the first piece gets to chill out, 2 sine x, times the derivative of cosine x, which is negative sine of x. So I end up with 2 cosine squared x minus 2 sine squared x. And then we can plug in 3 pi over 2. So f prime of 3 pi over 2 is going to be 2 cosine of 3 pi over 2 squared minus 2 times sine of 3 pi over 2 squared. Cosine of 3 pi over 2 is 0. I often draw this little unit circle with the 4 kind of corners of it so that I can easily see what sine and cosine are. So cosine of 3 pi over 2 is 0. Sine of 3 pi over 2 is negative 1. Negative 1 squared is 1. Negative 2 times 1 is negative 2. So you end up getting negative 2. So the equation of your tangent line would be y minus 0 equal to negative 2 times x minus 3 pi over 2. And you could probably, I mean, you could leave it like that, meaning you should erase the 0. If you've got y minus 0, you should just write y equals whatever. So y equals negative 2 times x minus 3 pi over 2. Or if you want to distribute the negative 2, it's negative 2x plus 3 pi. Which is probably a better way of writing the answer, but either way should be fine. I will point out, because this is worth noting, there is a trig identity for 2 sine x cosine x. And the trig identity is that 2 sine x cosine x is also equal to sine of 2x. And so then we could take the derivative. Well, the derivative of sine of some stuff is cosine of the stuff times the derivative of the stuff. So cosine of 2x times the derivative of 2x, which is just 2. Which is equal to 2 cosine squared x minus 2 sine squared x, right? There's a trig identity for cosine of 2x. It's equal to cosine squared x minus sine squared x. So if you multiply it by 2, you've got exactly that. And then you could plug in 3 pi over 2 and get cosine of 2 times 3 pi over 2 is 3 pi times 2. And cosine of 3 pi is, well, let's see, 0, pi, 2 pi, 3 pi ends me up over here, which is cosine of 3 pi is going to be negative 1. Oh, goodness. Sorry. Tried to get the answer out before I sneezed. So you get negative 1 times 2, which is negative 2, which is the same thing we got right here. So would I say this is easier this way? Maybe a little bit. If you know that this is equal to that, I would probably do it this way if I saw that. Because it's a little less work to take the derivative of this using the chain rule than it is to take the derivative of this using the product rule. Just a little, not a lot. Also, please interject, stop me if you have questions, right? I'm just gonna go. I got a lot of feedback in the reflections that people really like seeing me do just a lot of examples. And appreciate someone, which I totally get, whether they really appreciated not being put into breakout rooms where they're working with other people and nobody knows what's going on. They're just like sitting there wasting time. So I totally get that. Like, I do think there is some benefit to breakout rooms and working on stuff on your own, but I also understand that this might not be the best environment for that in general. Like in a regular classroom setting, I would totally have you guys actually work on problems for a couple minutes, and then I would walk around and look at what you're doing. And when we're back in the classroom, if you're back in the classroom with me, we will do that. But I kind of get it. Like the breakout rooms, it just feels like sometimes you're sitting there twiddling your thumbs like, what am I supposed to be doing? I'm not really sure. I would rather someone show me how to do this. That said, as I'm sure you're all aware, well, I'm not sure. I'm going to make sure you're all aware. You need to practice stuff on your own, right? Seeing me do it is great, but watching someone do math and actually doing the math yourself are two different things. And you have to practice it so that you're able to do it on your own when someone's not showing you how to do it. So really, I think you guys have homework in this class, so make sure you do the homework, but really sit down and practice this stuff. There's no substitute for practicing the math on your own. Trust me, I've watched a lot of people do math that I thought I understood, And then when I tried to do it, I was like, oh no, I need to practice this a lot. Even stuff I'm teaching, like the 21C stuff I'm going to teach later today, I need to sit down for a good half hour and be like, okay, how do you do this again? I have to practice it, because if you don't practice it, you don't know it. All right, let's look at some more examples. That one's kind of fun. Yeah, let's look at, checking off my list. Sure, let's do another trig one. Let's find the horizontal tangent lines. Let's find where f of x equal to x times 2. I feel like the 2 wasn't supposed to be there, but that's what the person wrote. X times 2 sine of x has horizontal tangents. It could have been sine of 2x. Oh, well, either way, it's a good question. Oh, no, I see why it might want to be 2 sine of x. Okay. So whenever someone asks where something has horizontal tangents, that's just code for take the derivative, set it equal to 0. So we're going to take the derivative. We're going to use the product rule. So I feel like it was written this way on purpose. So I'm going to think of it as that times that. So the derivative of x is 1 times the other piece not derivative, plus now x times the derivative of this, which is 2, derivative sine of x is cosine of x. I'm going to set this equal to 0. And now, so yeah, I don't know. This might be, I might be a little perplexed by this question. I think I see an answer, but I'm not actually sure. So yeah, let's factor out the 2 because we don't need that, or divide both sides by 2 even. Divide both sides by 2, I've got sine of x plus x cosine of x equal to 0. Yeah. I might turn to Desmos. So there is one answer that I can see for sure. X equal to 0 is definitely an answer. The sine of 0 is 0, and 0 times anything is 0. And after that, I don't know. So this is a time where graphical analysis is kind of helpful. So let's go ahead and take a look at Desmos real quick before we get too carried away here. So let me grab it here. Oh, come on. All right, one sec. Now, maybe I wrote down the question wrong, but I don't think I did. So let's go to Desmos and graphing. Share the screen. Sure, here's my screen. Let's graph. So I'm trying to see, I want to just know where that's equal to 0 instead of trying to see where the original thing has. Okay, so it definitely looks like that sine of x plus x cosine of x, that seems interesting. So a little bit bigger than 2. Yeah, I don't know how you would find that answer. That's really interesting. I don't know what, I feel like that might be pi over something, but I really yeah, that's a, and I believe the question was actually to find all values where it was equal to, where the derivative was 0 between 0 and 2 pi. Yeah, I don't know. I am a little stumped by that. I'm not sure how you're supposed to do that without a calculator or without something. Yeah, that's Yeah, I feel a little, I don't know how you're supposed to solve that without, I don't know what. So I really do wonder, and I'll have to go back and look at who sent me this question. I might have to ask them if I'm, I think I know what the problem is. I think I did write down the question incorrectly. I think it was actually supposed to be x squared times sine of x. That seems like a much more reasonable question. Sorry, I got that wrong. I must have missed the little caret symbol that someone wrote in their reflection. So let's go ahead and look at that because that is a much more normal. So good piece of advice, right? Yeah, no, that's okay. So if you see yourself getting something that looks weird, take a step back, right? Like I was like, this looks weird. I'm solving this, seems strange. Looking at the graph definitely showed me, yeah, those solutions don't seem like something we could find normally. Maybe we made a mistake somewhere. So it's really, really good to see that if you find yourself getting down a path that seems kind of strange, take a step back. Also, I should have included that writing it, right, x times 2 sine of x is not a typical way of writing that. If that was what we really had, I would have written it as 2x times sine of x. But it's probably x squared times sine of x. So then using the product rule, our derivative is going to be 2x times sine of x plus x squared times cosine of x. And this seems much more reasonable. Because now if we factor out an x, here's what we're left with. Well, I say this seems more reasonable before I actually see what the answer is. So factor out an x, we're left with 2 sine of x plus x cosine of x. This still seems a little, I don't know. I can definitely see that x equals to 0 as a solution, right? Because if x is 0, then what else you got? Yeah, I don't know. This x here is problematic. Yeah, I'm not sure. Sometimes questions are just a little weird. We can, again, if we look at this, I feel like it's not going to be super helpful. I'm just going to look real quick here. Yeah, those answers still seem very wonky. So if someone knows what the actual statement of this question was, oh, x plus 2 sine of x. Oh, that's so much. Okay. All right. We finally figured it out. Good. Because I was really worried that someone's asking you guys some crazy questions. Awesome. Let's get there for real now. This seems much more likely. Also, nice thing about this, it's okay. Some mistakes happen. This is much easier to differentiate. It doesn't require the product rule. It's just 1 plus 2 cosine of x. And now we do have to use our trig skills. So I'm going to try and figure out where 2 cosine x equals -1, where cosine x equals -1/2, which is where I thought we'd end up eventually. All right, so we do have to remember what cosine of some values is. So I'm going to remind everybody that cosine of 0 is 1. Cosine of pi over 6 is the square root of 3 over 2. Cosine of pi over 4 is the square root of 2 over 2. Cosine of pi over 3 is 1/2. And cosine of pi over 2 is 0. So of these 5 angles, the one that seems like it pertains to this problem is this one, where cosine of pi over 3 equals 1/2. The problem is we want cosine to equal -1/2. So what we need is the angle pi over 3 to be our reference angle, but we need cosine to be negative, which means we need to be in quadrant 2 or quadrant 3. Right? Since cosine is the x value, cosine is negative when we are on the left side of the coordinate system. There's a mnemonic device for remembering this. It is all students take calculus. All trig functions are positive in the first quadrant. Sine is positive, cosine and tangent are negative in the second. Tangent's positive, cosine and sine are negative in the third. Cosine's positive, sine and tangent are negative in the fourth. So I want where cosine is negative, so I want to be here where sine's positive and here where tangent's positive. So I need my reference angle, which is always measured to the x-axis, to be pi over 3. Oops, come on, James. Meaning I need my actual angle to be pi minus pi over 3 and pi plus pi over 3. So my actual answers here are x equal to 2 pi over 3, which is pi minus pi over 3, and x equal to 4 pi over 3, which is pi plus pi over 3. So although this question looks like a derivative question, I mean, it is a derivative question, the real point of this question was asking you to be able to solve this sort of equation, to be able to figure out where cosine is equal to -1/2. Yeah, okay. What time is it? Oh yeah, we got time. We got times. Let's look at this one, this one, and this one. Cool. Oh, I know. Yeah, there's some interesting questions here. I always think it's weird when you get asked questions like to take a derivative of a thing, but you aren't actually given the function. What I mean by this is something like this. We're given that h of 3 is equal to 7, and h prime of 3 is equal to -2, and we're given that f of x is equal to h of x divided by x, and they ask us to find f prime of 3. So before we can find f prime of 3, we have to find f prime of x. So the idea here is we're just going to throw the quotient rule at it, right? I've got the quotient. I'm going to do the bottom times the derivative of the top minus the top times the derivative of the bottom, all divided by the bottom squared. And then we can plug in 3. So I'm just going to literally plug in a 3 everywhere I see an x. So the f prime of 3 is 3 times h prime of 3 minus h of 3 times 1 over 3 squared. That's kind of it. And then we just evaluate. So I get 3 times h prime of 3, which is -2, minus h of 3, which is 7, all over 9. So I get -6 minus 7 is -13 over 9. So that's how we do a problem like that, right? They're just they're telling you how h works, even though they're not telling you what h is. And then they're just saying, take the derivative using the normal rules you know, and then throw in the values that we have. But I always feel like those questions feel a little kind of out there. Yeah, let's look at a couple more like that. People had a lot of questions about derivatives with square roots, which I feel like can be challenging. I mean, it's all challenging to some degree. You know, what's challenging is finding a pen that has ink in it in my office. That's what's challenging. Okay. Sure, let's start with this one. I think someone asked me this question. Find the equation of the tangent line to f of x equal to 5 over the cube root of x squared. Oh yeah, I saw this question and it looked like there was a mistake, and I don't think it was a mistake when they wrote it, because it looks like they did. I'm pretty sure I remember them just copying and pasting like the problem from whatever WebWork or whatever. It said at the point -1, 6, which worried me because -1, 6 isn't a point on this graph, right? If you plug in -1 for x, -1 squared is 1, cube root of 1 is 1, 5 over 1 is 5. So if this was you, I'll talk about what I think I would do. So I'm going to, the actual problem should be this. And then I'll talk about what I would do if this was what was actually written on the problem, and then how I would try and solve it. So first things first, we need a point and a slope. We have a point, kind of, right? And to find the slope, the first thing I'm going to do before I even try to find the slope is I'm going to rewrite this, right? Trying to take the derivative of that is, as written as it is silly. I don't want to use the quotient and the chain rule when I only really have to use the power rule. Right? We should rewrite this as f of x equal to 5 times, so this is the cube root of x squared, which is x squared to the 1/3 power, which is x to the 2/3 power. So in the denominator here, we have x to the 2/3, and then when it comes up to the numerator, it becomes x to the -2/3. So then we can very, very easily take the derivative. The derivative is going to be f prime of x equal to, the power comes down, 5 times -2/3 is -10/3, times x to the negative 2/3 minus 1 is negative 2/3 minus 3/3. And negative 2 minus 3 is negative 5/3. And then I plug in. Oh, this is a good question. All right, I kind of like this. So then I need to find the slope of the tangent line. So I'm going to plug in the point x equal to negative 1. So f prime of negative 1 is going to be negative 10/3 times negative 1 to the negative 5/3. Okay, here's a not super easy question to answer. What's negative 1 to the negative 5/3? Is it negative 1 or is it positive 1? Because those are your only options, right? When you have negative 1 to a power, it's either going to be negative 1 or positive 1. It's a good question. I see some guesses, some private guesses. So here's the thing. Let's compare negative 1 to the, so let's look at negative 1 to the 2/3. I'm ignoring the negative on the power for a second, versus negative 1 to the 5/3. Negative 1 to the 2/3, you can either do the power or the root part first, doesn't matter. Negative 1 squared is 1. The cube root of 1 is still 1. Or the cube root of negative 1 is negative 1, but then negative 1 squared is 1. Here, the 5/3 power, since both the numerator and the denominator are odd numbers, we're going to retain the negativeness. Negative 1 to the 5th power is negative 1 times negative 1 times negative 1 times negative 1 times negative 1. That's negative 1. And then the cube root of negative 1 is negative 1. So it's negative 1. So essentially, if you have negative 1 to a power, if the numerator part is odd, it's going to end up being negative 1. If the numerator part is even, it's going to end up being positive 1. The denominator part has to be odd for this to work. So this is going to end up being negative 10/3 times negative 1, which is positive 10/3. I should point out, right, the negative part of the power there just means it's the reciprocal, but the reciprocal of 1 is 1, and the reciprocal of negative 1 is negative 1, so it doesn't change anything for this particular type of thing. So then, the right answer would be y minus 5 equal to 10/3 times x minus 1. However, if the computer or the program or whatever already thinks that the correct point is negative 1/6, it might be, I don't know, but it might be that the correct answer that you have to put in is y minus 6 equal to 10/3 times x plus 1. I don't really know what exactly is going on there, but if I did this and tried it and it didn't work, because I was like, oh, I saw that the actual correct point should be negative 1/5. If this didn't work, I'd be like, well, maybe I should try this and just know that the program is dumb. And that's what I would say about that. Yeah. Look at some more examples. Let's see, I still have, so I've got a few more derivative examples, and then I'll try and hit some marginals and some motion stuff. Marginals and motion. Sure, that one. Yeah, we got that. Okay, let's do 3 more quick ones. So somebody asked me this one. What's the derivative of 7x to the 1/8 minus 2? This one is not too terrible. It's just the power rule, but the problem, the fractional ones are always kind of like, so we have to be a little extra careful when we take the derivative of x to a fractional power. It's going to be equal to, so doing it kind of showing all the work, it's 7 times, the derivative of x to the 1/8 is 1/8 times x to the 1/8 minus 1. And then minus the derivative 2 is 0. So then we should simplify this. 7 times 1/8 is 7/8. And x to the 1/8 minus 1, 1/8 minus 1 is 1/8 minus 8/8, which is negative 7/8. So I should write this as 7/8 times x to be negative 7/8. And then if I really wanted to, I would, some people prefer to write this as 7/8 times 1 over x to the 7/8, or 7 over 8 x to the 7/8. Any one of these ways of writing it is correct. I suppose you could even write it as 7x to the negative 7/8 over 8, right? Any of these are fine. It just kind of depends on what, right? If I was doing it, I would probably write it as this or as this. But any of them are really okay. Sure. One more, no, a couple more. Oh yeah, there were some repeated derivative things too. Let's look at that. So many things to look at. Sorry. So somebody asked about this one. To find for f of x equal to the square root of x minus 2 over the square root of x plus 2. To find f prime of 3. So if I was to find f prime of 3, right, you could use the limit definition here. You should not, right? You should only ever at this point be using the limit definition of the derivative if the teacher says use the limit definition of the derivative to find the derivative here. If they don't say those words, you should not be doing it that way, unless they've said you should do it all the time. But I really, really don't think that's what anyone means at this point. So I'm trying to find f prime of 3. I'm first going to find f prime of x. I'm going to use the quotient rule. I suppose before I find f prime of x, I'm probably going to rewrite this as x to the 1/2 minus 2 over x to the 1/2 plus 2. Because it's easier to take derivatives of things written as powers than written as roots. So it's going to be the bottom, x to the 1/2 plus 2, times the derivative of the top, which is 1/2 times x to the negative 1/2, minus the top, x to the 1/2 minus 2, times the derivative of the bottom, which is, again, 1/2 x to the negative 1/2. All divided by the denominator squared. Ugh, this looks terrible. And the really terrible part is that they gave you a number to plug in that's not nice. Like if you were plugging in 4, where 4 to the 1/2 is the square root of 4, which is 2, or if you're plugging in something like 25, where the square root of 25 is just 5, that would be not so terrible. But here, plugging in 3 is just going to look awful. I do think the intention of this problem is for you to simplify it a little bit before you plug in 3. You don't have to, but I really, if I was trying to answer this in whatever web work or web design, I don't want to have to type out square root of 3 plus 2 times 1/2, 1 over the square root of 3, right? It's just a lot to write. So let's simplify this just a little bit. When we distribute this, well, x to the negative 1/2 times x to the 1/2, when you multiply those things together, you add the powers, and negative 1/2 plus 1/2 is 0. So you're going to get 1/2 times x to the 0, which is just 1/2 times 1, plus 2 times 1/2 is 1 times x to the negative 1/2. Okay, this seems like it's maybe not terrible. Minus, let's just keep the minus out here, 1/2 x to the negative 1/2 times x to the 1/2 is again 1/2 x to the 0. And then minus 2 times 1/2 x to the negative 1/2 is minus 1 x to the negative 1/2. All divided by the same thing, x to the 1/2 plus 2 squared. So simplifying this a lot, x to the 0 is 1. So I get 1/2 times 1 plus 1 x to the negative 1/2. I could write that as 1 over the square root of x if I really wanted to, minus 1/2, and minus a minus is plus 1 over the square root of x, all over the square root of x plus 2 squared. So the 1/2 and the negative 1/2 cancel, and 1 over the square root of x plus 1 over the square root of x is 2 over the square root of x over the square root of x plus 2 squared. It's still not nice, but at least at this point, it's not terrible to have to write out. So if I was going to find f prime of 3, f prime of 3 would be 2 over the square root of 3 over the square root of 3 plus 2 squared. That's much less terrible to type in than square root of 3 plus, all of this. So yeah, you should probably simplify that one a little bit. It's kind of awful. I don't love that they don't know, that they sometimes just give us like, here's the thing, and plug in this ugly number and make it ugly. Sometimes I feel like sometimes it seems like not a lot of thought went into maybe writing the problem. Oh well, well, I mean, yeah, we'll have to deal with that. Okay, let's see. I think I had. Oh yeah, sure, go. Yeah, of course. Sorry. Yeah, I had one more. Let's see, let me see. I want to erase the other side. Those are erased. Okay, I'm gonna go to the other side. Here we go. I will post the video in case you need to go back and look at it later. I'll try and post it pretty fast. So here's another square root one or a root one. We have y equal to 3 over the cube root of x squared plus 8x to the 4th power. Okay, I have one more here. Oh yeah, fine. So for this one, again, it's really in our interest to write it so that instead of having it like this, you want to write it as 3 over x squared plus 8x. Okay, is the power 3/4 or 4/3? Well, let's see. It's a cube root, which would mean it's a 1/3 power. So right, it's going to be a 4/3 power. Yes, you could use the quotient rule here. No, you should not if you don't have to. Specifically, if you have a constant on top, like if this was like maybe x to the 3rd on top, I might not bring this up because I don't really want to use the product rule, right? So I'm going to write this as 3 times x squared plus 8x to the negative 4/3. But I'm just saying, right, like if instead on top I had like 3 plus x squared, I would probably just use the quotient rule. Because bringing this up to the top would then require this times that, which is the product rule. It's not really making it easier. But if your numerator is just a constant, it often makes sense to bring your denominator up to the top, having a negative of whatever its power is. So I'm going to do it like this and then just use the chain rule. So my derivative here, the constant multiple just hangs out. And the derivative of some stuff to the negative 4/3 power is negative 4/3 times my stuff to the 1 less power, so negative 4/3 minus 1 times the derivative of this stuff, which is 2x plus 8. And let's close that parenthesis. I would simplify this a little bit. You definitely should simplify this. And then I'm going to see that the 3's cancel here. So I'm going to get negative 4 times x squared plus 8x to the negative 4/3 minus 3/3 is negative 7/3 times 2x plus 8. And I would leave it like that. Okay. Let's see what I got here. There was one other, oh yeah, that's in my email, sorry. Someone asked about a problem that looked kind of like this. So what if I want to take the derivative of, well, actually I want to take the, yeah, okay. So sorry, let me back up. Really? Okay, fine. So I want to find the derivative, my function is tangent of 2x. And I want to find f prime of x and f double prime of x. And then they picked a stupid number to plug in, fine. So what's the derivative tangent of x? It's secant squared of x. So the derivative tangent of some stuff is going to be secant squared of your stuff times the derivative of your stuff, which is 2. Okay. There's not really any simplifying to do there. You can put the 2 in front, I guess, if you really want. We often do. I like to write it at the end to kind of emphasize the chain rule nature of the problem, right? You're multiplying by the derivative of the inside stuff, but then we usually put constants in front. So now for f double prime. It might be helpful to remember that this is 2 times secant of 2x quantity squared. So when I take the derivative, the constant multiple in front just stays, and the derivative of some stuff squared is 2 times our stuff to the first power times the derivative of that stuff. And the derivative secant of 2x, well, the derivative secant of some new stuff is secant of your new stuff, tangent of your new stuff, times the derivative of your new stuff. So simplifying this, I've got 2 times 2 times 2, which is 8. I've got 8 times secant is secant squared of 2x times tangent of 2x. What I really want to emphasize is be careful, right? When you differentiate secant squared, it's not secant tangent times secant tangent, right? It's secant squared, right? You have to use the chain rule. It's a little bit more complicated. Sorry, there's something else I want to mention here. Oh, and then this problem asks you to like evaluate this at some idiotic values. I'm not gonna lie, right? It's like find f prime of 6. Okay, well that's gonna be 2 times secant of 12 squared. Whatever secant of 12 is, I don't know. This is what I would type in for my answer, though, right? You shouldn't do. I don't think they want you to get a decimal approximation. If I was asked to find f double prime of 6, equally not very nice, right? You're going to plug in 6 and you get 8 times secant squared of 12 times tangent of 12. Yeah, kind of gnarly looking. Let's see here. Okay, sorry, let me do one thing before I forget. Okay. Let's see. I know I said stuff about marginals and velocity stuff. Sure. Let's see. I feel like we should do more chain rule stuff, but maybe I guess we can wait. Well, we'll hit the chain rule really hard on Thursday. Let's talk about. Let me give you a marginal example and a motion example. So marginals. Here's an example from the textbook. This is problem. Sure. This is problem 30 from chapter 2.3, section 2.3. Marginal revenue. The revenue in dollars is, so here's the setup. The revenue in dollars from renting X apartments can be modeled by R equal to 2X times 900 plus 32X minus X squared. And I'm sure they're imagining this as probably the profit or the demand function, like this is how much it costs when there's X units, and this is how many units are renting or something like that. So it's like the number times the price to get the revenue. We don't have to know that, but that's probably where they're kind of coming at that from. So they want to find, first the question is, what's the additional revenue from renting the 15th unit? Meaning, how much more revenue do we get when we rent so from the 14th to the 15th unit? So basically, we're trying to figure out what's the difference between renting 15 units and 14 units. They actually phrase it a little more specifically. Find the additional revenue when the number of rentals is increased from 14 to 15. So all we're doing there is figuring out how much revenue there is when there's 14, how much there is when there's 15, and subtracting to find the difference. This is not a calculus question, right? This is just to throw the numbers into the formula and see what you get. So we plug it in here. I guess I should get a calculator here so we can actually find some values. Plugging in 15, sure, we get, okay, fine. 32 times 15 should be 480. 900 plus 480 minus 15 squared is 225. That's going to be 30 times 1155. Sure, some really lovely number. And then when we plug in 14, the math is a little bit harder. So let's see. 32 times 14. Sure. Yeah, Minus 14 squared. And then add 900. And then multiply it by 28. Get 32,256. And the difference is going to be something really nice, 2,394. So I guess that's, I feel like it's expensive rent, but I guess things kind of cost that much. So yeah, all right. That is not that expensive rent probably for Davis, or at least, you know, in the realm of reasonableness, depending on how big your place is. All right, so then they ask us part B, what's the marginal revenue when x equals 14? Okay, literally all this is r prime of 14. That's it. And then now that I said that, let me go double check. I always feel like I make dumb mistakes when I talk about marginal revenue or marginal anything. No, yeah. The marginal profit is just, okay. Now I should say, when you're talking about marginal revenues, it's, you're kind of making the assumption that it's how much more revenue there would be when you increase by 1 unit. So that's why they're asking you to do this calculation, because they're asking you, let me back up 1 second. This is the actual calculation, right? This is actually how much more rent there would be if you increase from 14 to 15. The marginal revenue when x is 14 is a fancy word for the approximate increase in rent from the 14th to the 15th unit. So if someone says marginal whatever when you have a certain value, really all that's asking is approximate this change in value at this number. So this number we get should be close to this number here. It's a good approximation. It's easier to calculate. If I was going to calculate the derivative, I would probably multiply this out. I don't want to use the product rule if I don't have to. So let's write this as 1800x plus 64x squared minus 2x cubed. And then the derivative, r prime of x, is 1800 plus 128x minus 8x squared. If it were me, I would have picked a number like 15 because it's a little easier to plug in. But if we plug in 14, the numbers are still not great. It's going to be 1800. Sorry, I should have written 14 here. Wow, good job. Okay. 128 times 14 is something lovely. 1,792. 8 times 14 squared is 8 times 196, which is 1568. This is an easier calculation. I mean, it's slightly, it is a little easier than doing this minus this, but it's not a lot better in this particular example. Calculating this, we get, let's see. $2,024. That's a decent approximation of this number. Not great, but there are other examples where kind of the numbers for the actual difference are pretty gross and the numbers for the approximation are pretty easy. So that's kind of the point of marginals, is that the marginal whatever is going to give you an approximation of a change in 1 unit. And it could be a change of 1 unit, everything, right? It could be you're producing 1 more unit of a thing, or you're having 1 more unit rented, or right, or there's, you know, what else? I mean, there's marginal cost, where if you want to know how much more it costs to produce an extra unit, all that kind of stuff. Let's see. I don't think we have enough time to do a motion example. So let me throw 1 more marginal example at you guys, just because it seems worthwhile. Thursday, we will definitely do some motion examples, and we will also talk more about the chain rule. Let's see, what example do I want to do? I feel like that's a good one. Well, let's look at this one. This is problem 32 from the same section. The population of a developing rural area has been growing according to the model. So the population is equal to 22t squared plus 5t plus 10,000, where t is time in years. And then t equals 0 corresponds to the year 1990. So first I want you to evaluate p for different values. So the population at time equals 0, 10, 15, 20. We're not going to do all that. Let's just do a couple of them. So p of 0, clearly 10,000. P of 10, let's see, 10 squared is 100. 22 times 100 is 2200 plus 50 plus 10,000. Okay, great. That's going to be 12,250. Awesome. Let's leave it there. Determine the population growth rate. So dp dt, that's the population growth rate, right? The derivative is the rate of change. That's going to be 44t plus 5. It's not too bad. So let me ask you, what is, so this is a symbol for evaluating that. So what's the population growth rate when t is equal to 0? Well, that's going to be 0 plus 5, which is 5. What's the population? 5 people per year. That seems wrong. I feel like I must have made a mistake somewhere. Did I make mistakes? Doesn't look like it. Yeah, interesting. I guess, yeah, so sometimes the marginal is not good. So if you think about how many people actually grew from year 0 to year 1, right? In year 0, we have 10,000. And then year 1, we have 22 plus 5 plus 10,000. So our marginal there might not be super great, right? Because we're dealing with such small numbers, right? It actually grew by 27 people instead of 5 people. Okay, let's look at year 10. So the population growth rate at year 10, or the marginal at year 10, is going to be, well, if I plug in 10, it's going to be 44 times 10, so 445. How many people actually did we increase by from year 10 to 11? Well, for that, I have to plug in 11. Ugh. So P of 11 is some lovely number. Let's see, it's 22 times 11 squared, which is 22 times 100. Oh, I actually know that number. It's 2,662. How did I know that? Come ask me in office hours sometime. It's kind of a cool trick. Anyway, plus 55 plus 10,000 is going to give me, let's see, 717. Yeah, I don't feel like this marginal here is very useful. Sometimes the marginal is not a good estimate. Sometimes the equation you're working with is just so kind of different that it doesn't really give you a very good example there. Yeah, I wonder why this is. Oh no! Oh, I apologize. I was comparing this to this accidentally, or I should be comparing this to this. And the difference there. Okay, good. I was like, the marginal usually should be fine. If we compare the difference there, you get, yeah, the P of 11 minus P of 10 is 467. So yeah, this actual change in population is estimated pretty decently by that marginal.